In this video, we're going to look at Hess's law. Hess's law states, the enthalpy change accompanying a chemical change is independent of the route by which the chemical process occurs. Hess's law is used to calculate delta H for a reaction when we don't actually have the experimental data. How does this work? Let's say that we take a reaction that goes from reactants A to products B. We can actually use the delta H to figure out this process, or the enthalpy of this process, by going, let's say, from reactant A to intermediates, and then from intermediates to product B, as long as the intermediates cancel out and the overall process looks like reactant A to product B. It's easier to show than to actually describe, so let's work a problem. If we look at this example, use Hess's law to determine the enthalpy of combustion of ethanol. Here we have ethanol reacting with oxygen to give us carbon dioxide and water. To figure this out, we're going to need standard heats of formation for reactions that we can add up to come up with this actual chemical reaction. To do that, we'll need to find some. Now, when you start off, these will probably be provided, but you can also find these often in tables. Here are the three we're going to look at. Carbon plus oxygen going to carbon dioxide with a delta H of minus 393.51 kilojoules. Oxygen plus hydrogen going to water with a enthalpy of minus 285.83 kilojoules. And carbon, hydrogen, and oxygen going to form ethanol with an enthalpy of negative 277.69 kilojoules. What we need to do is take these three reactions and modify them so that it will give us the original reaction from the problem, the combustion of ethanol. So we'll look. On the product side, in the combustion of ethanol, we see two carbon dioxides. If we look at our three reactions here, we see carbon dioxide is in our first reaction. But we had two carbon dioxides, which means we're going to take and multiply the entire reaction and the enthalpy by 2. This will give us 2 carbon dioxides so that we can match our original reaction. If we look at our second, we have liquid water. Well, we had liquid water in the combustion of ethanol, but we had 3. So since we only have 1 here, we're going to need to multiply the entire reaction by 3, including the enthalpy. Now, those were the products that we had in our original reaction. If we look at our third, we have ethanol. But the problem here is that ethanol is a product, but we want ethanol to be a reactant. So therefore, we're going to have to reverse this reaction, which means that we're also going to have to change the sign of our enthalpy. So let's do that. Let's multiply the first one by 2, the second one by 3, and let's reverse the third and also make sure we change the sign. Now you can see that we have multiplied the first one by 2, the second one we multiplied by 3, and the third one we've reversed. You see the changes in our enthalpy. Now what we want to do is make sure that what we have here is actually going to be the reaction that we want to calculate. So we didn't have carbon in our original process, so let's see if there's a carbon here. Well, there's carbon and 2 carbons, so we can cancel those because they're on both sides. One is a reactant, one's a product. If we look at hydrogen, we see that hydrogen also cancels. One is a reactant, one's a product. We have oxygen as reactants and oxygen as products, but we can see that they don't have the same quantity. But we can take 1/2 off here, which means we'll have just 1 there. Now, if we go down and add up all of our reactions, we'll see that we start with ethanol. Then on our product side, we have 3 oxygens, we have 2 carbon dioxides, and we have 3 waters. Now, what we do for enthalpy is we have the correct reaction, so now we can just add up all of our enthalpies. That's going to mean that we have a total enthalpy for this new process of minus 1,366.82 kilojoules. It's important that you double check. It's important that if you reverse reaction, you make sure you reverse the sign of your enthalpy.